So we're gonna get started with the 5-step process of what I think about when I do spectroscopy problems, right? So the first thing that I do is I calculate the degrees of unsaturation. Yes, and do you remember the equation for that? Like, does Kaggle make you memorize it, or?
We have it on paper.
Uh-huh.
C equals 2 plus
2c plus 2 minus h minus x plus n all over 2. Yes. And what degrees of unsaturation would tell you is how many double bonds you have, how many rings you have, and how many triple bonds you have, right? So let's see if we have a double bond, a triple bond, and any kind of ring like this, right? If you have a double bond, that's going to give you 1 DOU. Yes. 1 pi bond, right? What about a triple bond? 2. Yes. Any ring? Just 1, yes. So if you have like more than 4 DOU, or at least 4 DOU, you're gonna most likely have something called a benzene ring, right? Because there's 3 double bonds and 1 ring. 3 plus 1 is 4. So when you have at least 4 DOU, then you most likely have a benzene ring. The next thing I look out for is the IR, right? And this IR here is going to tell you what functional groups are present, right? Functional groups, right? And the third step that I do is I then look at my HNMR to see this very specific fragments of the molecule, right? Because HNMR is the most powerful tool here. It shows you how many neighbors each peak of hydrogens has. Hello. And the integration with them as well. So I'm gonna go more into this, but the 3 things that I look for HNMR are the de-shielded versus shielded regions, right? De-shielded. That's the most important part. Well, to look at the beginning, de-shielded versus shielded. Okay. And then I look at the integration, right? How many hydrogens are in a peak, and then I look at the n+1 row coupling, number of neighbors, right? And then after I piece my fragments together, I then connect the fragments. And then this could be a lot of trial and error here, right? And you just pray too, because it's gonna be very difficult on piecing those fragments together in this very specific molecule that she wants in the answer, right? And then the 5th step, the last step here, is to verify with everything that you have, right? You're gonna verify with the DOU, the chemical formula. That's a very big one, right? Because that keeps track of how many atoms are there in the molecule, like how many carbon atoms are there, how many halogens are there, hydrogens, oxygens, right? Chemical formula, the IR, and the HNMR, and then hopefully you get the right answer, right? So this is like the 5 steps that I go through to solve the spectroscopy problem. So looking at this problem here, our chemical formula is C14. Do you guys still need this? Try. Okay. Okay. Let's see. Let me erase this here. Okay. Yes. Okay. So we have C14, H28, O3. So when we calculate the DOU, that's going to be 2 times 14 plus 2 minus 28 minus 0 because there's no halogens, plus 0 because there's no nitrogens, all over 2. So 2 times 14 is 28. 28 minus 28 is 0. So it's going to be 2 over 2, which is 1 DOU. Yes. So we could either have 1 double bond or 1 ring, right? Now we look at our IR next. So there is a very specific graph of IR that I like memorized. But do you know what functional groups are gonna be represented by what in the IR? Like the shape of the peak, is it sharp or broad? Oh, those ones right there. Okay, let me briefly go over with you what the IR would be, and then we can analyze the IR right there. So the IR is gonna have this graph right here, right? And then let's say this is the 1500 peak. Ignore everything 1500 and below, right? There's a very specific region of that graph, and that is called the fingerprint region.
Okay. So 1500 and below.
Yes,
We ignore.
you guys ignore, yes, because that's going to show signal bonds like carbon single bond oxygen, carbon single bond carbon, and we can't really get anything useful out of that region because that's called the fingerprint region. Does that sound familiar, the fingerprint region? Yeah. Okay. Now, let's look at the 3000 peak. Right. This 3000 peak here, you're most likely going to have a jagged peak like that. Right.
Yeah, like here.
Yes, like that. That represents your sp3 carbon hydrogen bond. Those are your normal bonds like that. Like this is an sp3 carbon. This is the bond from an sp3 carbon to a hydrogen. So almost all your molecules will have this peak right here because we almost always have this bond right here for all molecules. Right? So this is almost always going to be there for most molecules. Now, let's go to 1600. Around 1600, if you see a sharp peak there, that's going to represent a carbonyl, carbon double bond oxygen, right there. At 1700, if you see a sharp peak there, that's going to flip that, right? 1700 is the carbonyl, the carbon double bond oxygen. The 1600 is the alkene, carbon double bond carbon. Yes, that's the alkene. 1600 is alkene, 1700 is carbonyl.
So it's CO, right?
This is CO, yes. The 1700 is CO. Yes, nice catch. Yeah. C11O for 1700, C11C for 1600. Okay. Now, at around 2100 to 2300, right? Say 2100 to 2300. If you see a sharp peak around there, that's your alkyne region, your triple bond region actually. C triple bond C or C triple bond N. So it could be an alkyne or a nitrile, right? Now, if you see a peak at around 2700 and you see like a sharp peak there, that's going to be your aldehyde functional group. So when you see a sharp peak at 2700, a little bit to the right of 3000, that's going to represent your aldehyde. Right. Now, let's look at 3300, this range right here. This is when it gets interesting. When you have a big broad peak at 3300, yes, that is OH, alcohol. When you see a double fang molecule like this, that is also a little bit broad, that is NH2.
Could it also be NH?
NH is going to be also this big broad peak right here, right? So this big broad peak here can represent OH or NH, yes, right? Because the broad peak represents hydrogen bonds. This NH here only has one hydrogen bond. That's why we only see one big broad peak. NH2 has two hydrogen bonds. That's why we see two broad peaks right there. Now, if you see a sharp peak at 3300, right? This is going to be around 3300. That's going to represent your terminal alkyne. meaning that the alkyne is at the terminal end of the molecule. It has that hydrogen right there, right? There's two types of alkynes you can have, an internal alkyne and a terminal alkyne. This is an internal alkyne. This is a terminal alkyne. Right? Internal meaning that it's inside of the molecule.
And the both sides have a C.
Yes, both carbons here are Cs.
Okay.
Right? C triple one C, C triple one C. But this C triple one C here is inside of the molecule,
Okay.
on the internal side of the molecule. This C triple one C is at the terminal end of the molecule.
So the internal one, the internal alkyne is at the 100 to 2. So the internal alkyne is here.
Yeah, 2,100 to 2,300. Yes. But when you have a terminal alkyne, right, you're gonna have two peaks. You're gonna have that 2,100 to 2,300 because that peak represents the C triple one C. Both alkynes have that C triple one C.
Okay.
But the 3,300 sharp peak right there represents the C triple one C attached to a hydrogen, and only the terminal alkyne has that peak.
Okay. So
Right.
if we have both, then it's terminal.
Yes.
If we only have one, then it's internal.
And it has to be this one here.
Okay.
Then it's internal. Yes. Right. So when you see this, you always see this with this, like they're always paired together. Right. Same as this right here. If you have this aldehyde peak right here, what peak will this pair with? Right here. Like this aldehyde. It's gonna be somewhere around here. This aldehyde peak at 2700. What is this functional group right here?
CO.
C11O.
Oh, I see.
Yeah, so when you have an aldehyde, you're always gonna have two peaks. This 1700 sharp peak and that 2700 sharp peak. When you have an aldehyde, those two peaks will always pair up with each other as well. Right? Let me airdrop you guys a cleaner chart of this because this is just like based on my memory of it, but here is a chart that I made before, so then you guys have a cleaner chart here. Are you guys from 118A? I see.
Actually 8B,
8B?
here it's going to be alpha.
Yes, it will because you guys learned about alcohol reactions, right?
Yeah, we actually start with alcohol.
Alcohol reactions, yes. 118A is also alcohol reactions, so we'll get there to the alcohol reactions as well. Are you from 8B as well?
18A, yeah.
Oh, 118A as well?
118A, yeah.
Oh, yeah, Cagley or Levens? Cagley? Okay. Let me airdrop the spectroscopy thing. Spectroscopy. Content. Actually, I have it on my. Okay. So, moving on. Anything else from the IR chart? 3,300 sharp peak, 3,300, 2,700. I think that's it from that chart, right? Okay, so now let's look at that spectroscopy problem that we were working on right here. 1,500 right here, ignore everything here.
Yeah.
That's the fingerprint region.
Yeah.
This right here is going to be 1,700 because it's like in the midway point between 1,500 and 2,000.
So C double bond O.
Yes. So from the IR, we know we have a C double bond O. That's good. Now this 3,000 peak right here, that's the regular sp3ch. We can basically ignore that.
Wait,
What?
Why do we need to?
Well, you don't ignore it, but it's not going to give you an important functional group,
Oh, I see.
right? Because that sp3ch is this regular
Okay.
carbon-hydrogen bond, that's single bonded. That's still important, but it's not a functional group, like a carbonyl or an alcohol, right? Now, if we have this broad peak at 3,300, what functional group does that
OH.
represent? OH, yes. So we know we have an OH as well. So we have two functional groups ready, carbonyl and OH. That's going to be worth points. DOU is worth points. Your functional groups is worth points. Not for Wiley, because, yeah. Okay. So that accounts for our one DOU because we already have that double bond. Yes. And we see that we used up 2 oxygens already. We have 3. Yes. So we have 1 more oxygen somewhere. But we'll worry about that later. Now let's move on to the HNMR. Is it okay if I erase this?
Yeah.
Here? Okay. Let me erase this.
I'm
Here.
really confused about
The HNMR. Oh my gosh. Okay, let me go over the HNMR regions that I also have here. 0 to 2, that's the boring region. Right? That's the regular carbon-hydrogen bonds like that. No electronegative atoms nearby. 2 to 3, that's the alpha region, meaning that the hydrogen is going to be alpha to a pi bond, right? This is an alkene carbon right here. This is the alpha carbon, meaning the first carbon away from the alkene carbon, yes. So that's the alpha hydrogen right there. We can also have this alpha carbon, which is one carbon away from the carbonyl. A carbonyl is a carbon of one oxygen, right? We can also have a hydrogen alpha to an alkyne, like that, right? And now a terminal alkyne hydrogen will actually be in this region as well, right? This hydrogen here will count in the 2 to 3 region as well. Okay, this is the sneaky one here because a lot of people like don't overlook this alpha hydrogen right here, which is one carbon away from a pi bond, like an alkene, carbonyl, triple bond, or part of a terminal alkyne hydrogen, right? 3 to 4 is going to be the electronegative region. That's when you have a hydrogen bonded to a carbon that is bonded to an electronegative atom X. And X here can be oxygen, nitrogen, chlorine, bromine, iodine, fluorine, right? Any electronegative atom you have in the chemical formula. That's around 3 to 4. Right? 4 to 6 is going to be the alkene hydrogens. So when you have an alkene like that, the hydrogens directly bonded to the alkene carbon is going to be between 4 to 6. Right? So let me actually circle the hydrogens in red where these will be in the HNMR. Right? This hydrogen here is different than this hydrogen right here.
Because that is connected to the alkene.
Yes, that is directly connected to the alkene bond, which is going to be between 4 to 6. Whereas this one here is one carbon away from the alkene bond. Yeah. Now, 6 to 9, right, this is not the scale, is going to be the benzene hydrogens. So when you have a benzene, the hydrogens directly attached to the benzene are going to be between 6 to 9. Right? That's different than this hydrogen. Even though this hydrogen here is bonded to a double bond, this double bond here is part of a bigger thing here, the benzene. Right? This alkene here is not part of a benzene, so that's going to be between 4 to 6.
Okay.
Now, if you see something between 9 to 10, usually 10, that's going to be your aldehyde hydrogen. Now, 12 plus, that's the most de-shielded functional group you have, which is the carboxylic acid. And notice how the more de-shielded we get, the more to the left side of the graph we get, it's easier to distinguish between the hydrogens, right? Over here, everything on the right side, it's so clumped up together, so broad, yes. That's why this is the more fun region, the easier region to look at in HNMR, right? And let me also mention that this region here going to the left is going to be considered de-shielded or downfield. The region going to the right is going to be shielded or upfield, right? And to conceptually understand like what's going on behind the scenes, you could think of it like this. Imagine this hydrogen here is bonded to a carbon, a non-electronegative atom. This hydrogen here has electrons around it. And what HNMR does is that HNMR tries to shine magnets through the molecule and read the hydrogen atoms. This hydrogen here is not read easily because electrons are shielding it from the magnet. That's why it has a low ppm value. Whereas if you have a hydrogen here attached to an electronegative atom, electron withdrawn group, the electrons are going to be withdrawn towards the electron withdrawing group, and when the magnet from the NMR shines through the molecule,
It's D-shielded.
it's de-shielded by the electrons, picking up this hydrogen more easily, having a higher ppm value. It's more visible in NMR, right? So that's why this region here is more de-shielded when there's more electronegative atoms, electron withdrawing groups around. Okay. Now there's another thing. Between 0.5 to 5, when you see like a broad peak like that, that's going to represent your alcohol or NH group, right? Alcohol or NH. Or if you have two hydrogens that are broad, it could be NH2, right? And the reason why is because, like we said earlier, when you have a broad peak, that broad peak is represented by a hydrogen bond.
So you said 0.5 to 5.
Yes, 0.5 to 5, but you're most likely going to see it between 4 to 5, that broad peak. But this is a conceptual thing for Levens especially, because she's going to ask, like, what peak will you see the alcohol in or the amine in? And the correct answer is 0.5 to 5, but that's just a nitpicky thing. Right? But when you're actually putting it to practice, the broad peak is going to usually be between 4 to 5, that broad peak there, which represents an alcohol or amine. So based on what we analyzed from the IR, we know we have an alcohol. So in the HNMR, we expect that broad peak somewhere. Do we have that broad peak in the HNMR?
This one.
Yes, it's that one, that broad peak there. So it's 0.5 to 5. That's in that range.
Okay.
So that's going to be the alcohol.
Okay, and it's
Hydrogen.
usually only 1H because it's OH.
Yes, 1H. Or it could be NH as well with 1 hydrogen. Right? If you see 2 H's, that's gonna be NH2. And there's gonna be some problems that has 2 H's that are broad, and that's a big sign that it's NH2. If you
So
see
if
2H.
it's just one broad and then this says 2H, then it would be NH.
2. Yes. Yes. Okay. So you guys need a picture of this HNMR graph. I think you guys have a note card, right? Like you guys have a note card of all these regions already, so you guys don't need this. Yeah. Yeah. Okay, so we're gonna go back to this chart to analyze that chart right there. Okay, so I'm gonna erase this and then we can analyze that right now. Okay, so this is our HNMR. We know this is alcohol right here. What I like to read first is the most de-shielded region,
Okay.
which is this peak at 4 right there.
Yep.
Right, so this peak at 4. Alkene is between 4 to 6, so it would be a little bit higher, right?
Oh,
I would say this is next to an electronegative atom.
okay.
Like in this case, oxygen, because based on the chemical formula, our most electronegative atom is oxygen, right? So,
Okay.
and we also know we have no alkenes in the structure because on the IR we had no short peak at 1600.
Okay.
So we could rule out the alkene,
Okay.
right?
So it has to be something.
Yes. So I'm gonna draw that oxygen out like that, and I'm gonna draw out a carbon right here. The 2 hydrogens right here in that peak are gonna be represented like this. H, H. Those are the 2 hydrogens here. How many neighbors would those 2 hydrogens have based on the suffix we see here? 2 neighbors, right? Because n plus 1, 2 neighbors plus 1, that's 3 subpeaks, right? So when we extend that out, this is my fragment. Because it's 2 neighbors are gonna be, like neighbors, we count that by 3 bonds away. So coming from the hydrogen, 1, 2, 3. That hits a hydrogen, so that's a neighbor. 1, 2, 3. That hits a hydrogen, that's a neighbor. So there's 2 neighbors here. I don't know what's connected to here yet, but that's why I'm drawing a squiggly line there to show that this is a fragment.
I'm confused about. I'm really
Uh-huh.
confused about the neighboring.
Oh, the neighboring stuff? Yes. So let me show you the example. This is just an example here. Let's focus on this structure here. And let's look at these 2 hydrogens right here. To count how many neighbors these 2 hydrogens have, you count 3 bonds away from the hydrogens. right? These two hydrogens here are part of one peak. 1, 2, 3. That's a carbon. That's not a neighbor.
That's not a neighbor.
Not a neighbor because that's not a hydrogen. A neighbor would be a different hydrogen.
Oh, I see. So
Right.
aren't there hydrogens bonded to that?
To this carbon?
Yeah.
Yes, it is. That's the neighbor that it has, right? Because if you go 1, 2, 3, that hits a hydrogen. That's one neighbor to that peak right there.
Okay.
1, 2, 3. Is that a neighbor? No. And that's all we can go to, right? Because carbon, carbon, hydrogen, that counts. Let's go here. 1, 2, 3. Is that a neighbor? No. 1, 2, 3. Is that a neighbor? No. Even though there are hydrogens here, they're too far away to be considered neighbors. So these two hydrogens here only has one neighbor. And on the HNMR, what that will show up as is going to be following the n+1 rule. N represents neighbors. Because this peak only has one neighbor, we plug 1 in to n. 1 plus 1 is 2, which is going to be a doublet. And it would look like that for this peak. Right? This doublet here shows that this peak has one neighbor.
Okay.
Right? n+1 equals subpeaks. So if you read it from the graph, the HNMR graph, if you want to read the number of neighbors,
It's a number of peaks minus 1.
yes,
Okay.
neighbors equals number of subpeaks minus 1, which is how we were able to get 2 neighbors off of this peak. Because it has 3 subpeaks. 3 subpeaks minus 1 is 2. That's why we know that there's 2 neighbors based off of this 2 hydrogens right here. And those are the 2 hydrogens right here.
Okay.
Right.
Yeah, I see.
Do you understand why I had to put these 2 hydrogens next to this oxygen? Mhm. Think about the de-shielded versus shielded region, right? If we have 2 H's here at around 4 ppm, that's going to be de-shielded next to
Yeah.
electronegative atom. If that oxygen was not there and it was a carbon, this peak would be way more shielded, way more to the right side if the oxygen was not there.
Oxygen is electric.
Yes, because oxygen is electronegative, right? Okay. Now, from here, that's that peak right there. And this right here, like it could be an ether, or it could be my OH, alcohol. I don't know yet. I'm gonna go back to this peak. I don't know what this is yet. Right. Now let's move on to the next peak. That one right there, between 3 to 4. So that's gonna be 2 H's.
So that's gonna be 2 neighbors.
Uh-huh.
Wouldn't this
2
also
neighbors.
be something that
Has electronegative atom.
X?
X, yes. And so that around like 3.3, let's say, also has this 2H. So it could also be like this as well. Right? And this could be my ether or alcohol. I don't know yet. Okay.
So it's the same thing.
It's the same thing.
And then this, we already said it's an OH.
That is an OH, yes. That around 2.7, that broad peak right there, that has 1 H, is the OH alcohol right there. Right? And we have our 3 oxygens accounted for. 1, 2, 3 from the O3 and the chemical formula right there. Right? Now, the next thing is looking at the common patterns, right? And I'm going to show you guys this here. If you have an isopropyl group, you're going to have this pattern right here. Right? Like when you see this 6H doublet here pairing with this 1H multiplet, you most likely have an isopropyl group in your molecule. Right? And here's the reason why. These 3 H's here and these 3 H's here are one peak. They're symmetrical. Like they have the same chemical environment. And the way to visualize that is that this is going to be single bond. if you visualize that single bond rotating, right, like with the model kit, this group here and this group here are gonna rotate into each other's spots, right? So that's why these three hydrogens are gonna be have the same chemical environment as those three hydrogens right there. And let's say that's the green peak right there. That's gonna be these 6 H's here, because these 6 H's only have one neighbor, and that's the one neighbor right there, right? Because you go 1, 2, 3, neighbor, 1, 2, 3, neighbor, right? Now this 1 H here is gonna have at least 6 neighbors, 1, 2, 3, 4, 5, 6 neighbors, right? Which is why it has a lot of multiplets right there. I drew out 8 subpeaks here, meaning that it has like 1, 2, 3, 4, 5, 6, 7, 8, 7 neighbors, right? And to have it 7 neighbors, there would have to be 1 hydrogen right here, right? If you see 9 subpeaks, 8 neighbors, there would be 2 hydrogens here. Yes. If you see 7 subpeaks, 6, there would be 0 hydrogens here, right? So this could be different actually, right? But if you see a 6H doublet with 1H, lot of subpeaks right there, big sign there, you have an isopropyl group on your molecule. Another common fragment that you'll see is a tert-butyl group.
Is that what?
Tert-butyl, yes. And it's gonna look like this. How many neighbors does this peak have? 0. Those 9 hydrogens are these 9 hydrogens here. 3, 6, 9. These 6, 3, 6, 9, like 9 hydrogens here in this peak has 0 neighbors. Because if you go 1, 2, 3, that's gonna be a carbon. That doesn't count. There's 0 hydrogens on that carbon.
I see. Okay.
Right. The 9 H's here, or these 9 H's are the tert-butyl group with a big singlet peak right there. The height of the peak represents how many hydrogens are in the peak. That's why 9H here has a very long peak, because there's 9 hydrogens there. That's the integration part of the HNMR. So just keep that in mind when you work through practice problems, because when you see something like this or this, you know you have either isopropyl group or tert-butyl group in your molecule. And draw that out, because that's going to be worth points as well. Right. Okay. So the next thing here is going to be this one, yes. And that's between 2 to 3, which is the alpha region, right? So we have a pi bond here, the carbonyl bond. Let's say it's 2 to 3, like let's say 2.1. 2.1, and it was 2 H's with a doublet. 2 H's with a doublet. I'm just gonna draw in the carbonyl right here, right away. And then I'm gonna draw out the 2 H's here right away. Right, because this is the carbonyl carbon, this is the alpha carbon. The alpha carbon here has 2 hydrogens, which is gonna represent this peak right here. With how many neighbors based on this number of subpeaks? 1 neighbor, yes. So my fragment is gonna look like this, because these 2 hydrogens here, if you count how many neighbors it has, it will only have 1 neighbor. 1, 2, 3. There's an invisible hydrogen there, right? I had to expand this fragment out, because if I did not expand that fragment out, right, like let's say I didn't add that group right there.
It would have 2.
Yes, and that's not right, because we see on the number of subpeaks here, we see how many neighbors it has specifically, which is 1 neighbor, right? So that's why I had to expand this fragment out here. And what does this look like based on the previous structure that we got? Right. We see that 6H there with a doublet, and we see this 1H here with how many?
So that's a isopropyl.
Isopropyl group, right? So that's gonna be this peak right here, this fragment right here. But how many neighbors does this 1 hydrogen have right there? Hi. 118A and 8B right now.
Okay.
Yeah.
B?
8B.
8?
8B, 118A right now. Yeah.
Do you have 18B?
later. 3:30 to 5:30. Yeah.
This has 8.
This has 8.
9.
9.
So
1.
8 neighbors.
2, 3, 4, 5, 6, 7, 8, 9. Yes.
He's doing like.
So because there's 8 neighbors, right?
Yeah.
I'm just automatically gonna cut off the fragment right here. This is just like a guess right now. I don't know if this is true or not, right? I'm gonna say this is my isopropyl right here, where my 6 hydrogens, 1, 2, 3, 4, 5, 6 hydrogens, is this 6 hydrogens right here.
I usually got more than 20.
Because it has one neighbor,
Okay.
right? And its one neighbor is right here. How many neighbors does this one hydrogen have?
Wait a second.
Uh-huh, yeah. Take some time
Wait a
to
second.
think about it.
So that hydrogen has. Oh. I'm so sorry. Does it have to be 3 bonds?
3 bonds away. Yeah, so it might help if I draw out all the hydrogens nearby. We're focusing on this one hydrogen and its neighbors. Here, you could see, you could try, let me see what you're thinking about.
So this is 1. This is 1.
Uh-huh.
This is 1.
Yeah, so that's 3 right now.
3, 4,
Mhm. 5, 6.
and then 7 and 8.
Yes.
Oh, and that's the 9.
Yeah. 9 subpeaks for that one hydrogen right there. Yes.
Okay.
Yes. So I'm just connecting my isopropyl group here right now.
Okay.
Right. And the 2 H's here has one neighbor, which is that one neighbor right there. Okay.
Okay.
So this is the end of the molecule because we cannot continue on anymore. We can add more groups here.
Yeah.
This is the end of the molecule.
Yeah.
Okay. Now what I also like to do is I like to cross out all the peaks that I used up already. So just imagine visually, or if it helps, like cross out that peak, cross out that peak, cross out that peak,
Okay. That's
cross out that
done.
peak.
That's done.
And this is done as well. Yeah, now we got these peaks to worry about.
Mhm.
Let's look at this one here, because the 2 H's here, like those are the most problematic ones. Like I do that at the very end, because
Okay.
those gonna be like the 2 H's in the middle of the chain. That's confusing. So let's look at the 6 H's here. How many neighbors do those 6 H's have? 2 neighbors, yes. Hold on, let's see here. 2 H's here, oxygen, alcohol. 6 H's, 2 neighbors. I'm trying to think about. Shoot, this might be a symmetrical molecule then. If it's 6 H's with 2 neighbors. Wait, 6 H's, 2 neighbors. I'm getting stuck here. Yeah. I'm gonna go back to this. This is 4. Oh, this definitely is symmetrical. Because yeah, we have 4 H's and 6 H's, 2 neighbors here. I'm just gonna start drawing random things and praying. I don't know yet. So I know that my molecule has this. Ooh. I think this is gonna be somewhere in the molecule, because these 6 H's right here are going to be chemically equivalent. The reason why is because think of this as a single bond that's going to rotate. When they rotate, this whole ethyl group here and this whole ethyl group here are going to rotate into each other's spots. So these 3 hydrogens here are going to be here. These 3 hydrogens here are going to rotate here. So they're the same. How many neighbors do these 3 hydrogens have right here? Focus on these 3 hydrogens. How many neighbors do these 3 hydrogens have right there?
2.
Yes. That's this peak here with 2 neighbors.
Because they have 6 hydrogens and 2 neighbors.
Yes. Right. But this right here counts as 1 peak. But they have 2 neighbors right there. But how many hydrogens are in this peak right here. Are there hydrogens equivalent to these hydrogens? Hydrogens that are the same as these hydrogens? Those. That's four. Four hydrogens. Which is the four hydrogens peak you have on the HNMR?
So this?
Yes. How many neighbors do those have?
3.
Three. And we see that it's the three hydrogens right here. Right? And it's also between 1 and 2. Okay, so we know that there's going to be 0 hydrogens right here.
Yeah.
Because we already have 3 hydrogens right here. But that's accounted for. But I can't put the carbonyl here, because if I put the carbonyl here, that's going to be the alpha carb. Wait, actually, I can actually. Wait, what's going on? 1, 2, 3. Yeah, this is a big one. Yeah.
Oh, I really
Yeah.
hope that it's not.
1, 2, 3, 4. Yeah. The vocab questions, it's just a spectroscopy problem like this. It's pretty hard. 1, 2, 3, 4. Yeah. I'm gonna erase this because that was just me explaining how to count neighbors. And I'm gonna start connecting things and praying.
This is so
You need to double check based on all the carbons.
Yeah. We have 14 carbons in the chemical formula. We used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. I'm just gonna connect it like this somehow. Yeah. So I'm just trying random things here. I don't know if this is right. I'm just trying random things here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm missing 2 carbons. I'm just gonna try. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And we might have an alcohol here somewhere. Yes, there has to be an alcohol, right? And we also have an isopropyl group as well, so I have to take that into account as well. Oh, the isopropyl group's right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm gonna put the alcohol group right here for now, but I don't know if that's right. The reason why I'm putting the alcohol right there is because you know how we have 4 hydrogens here? 1, 2, 3, 4, like in the same peak, and they have 3 neighbors, and those are the 3 neighbors here. I don't want any hydrogens here,
I see.
so I had to put an alcohol right there or some other group there to prevent the extra neighbor right there, right? And we got this peak accounted for, 2 H's here with the neighbors. There's one more oxygen missing, right? It could be this right here. 2 hydrogens.
Were we
Let me
supposed
see.
to do this?
Yes,
This one?
we need an
It
oxygen.
could be ether or ester.
Yeah, it could be ether or ester.
For the extra carbon.
Yeah, I know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Missing 1 carbon here. Right? Let's see. This looks wrong here. 2, 4, 6. I'm gonna look at these 2 hydrogens here with 2 neighbors. 2 hydrogens here with 2 neighbors. 2 hydrogens with 2 neighbors. Yeah, 1 and 2, 1 and 2. Oxygen. two neighbors. Huh.
So then this got two neighbors, this got two neighbors.
These will have two neighbors. Oxygen here, like in the middle.
Yeah.
Yeah. Let's try that. Okay. Let's try it.
Try that.
Yes. Let's see. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But I'm still missing a carbon in here.
I remember like building like somewhere in 90.
Okay, can I see the paper really quick?
Well, you guys are
Hydrogens,
one building is some
4 hydrogens,
when you guys
isopropyl,
you guys are still fighting each other.
2 hydrogens here with 1 neighbor. We have an alcohol, and we have 3 oxygens. So this is most likely the oxygen right here. I'm gonna erase this whole thing. And then put the 2 hydrogens there with 2 neighbors. These 2 neighbors here are gonna be
So we're allowed to take like a whole page of
2 neighbors with 2 neighbors like that.
that's pretty bad.
And then we're gonna put
I might need to check how small I can write. And real magnify.
an OH
You know what?
right here somehow. 2H, 2H. This is crossed out. This is crossed out. This is crossed out. This right here is going to be that oxygen right there. And then this is 1, 2, 3, 4. But we can go over alcohol reactions for 8B after this problem here. Like if you guys have any alcohol problems you want to go over. 1, 2, 3, 4, 5, 6, 7, 8. One, two, three, four. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's good. 28 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Good. 3 oxygens. 1, 2, 3. Good. Yes. I know. I was like, this is not working well, so I had to like restart everything. I know this was here for sure, for a fact, and I just put an ester right here because that's the most common pattern. We have like multiple oxygens, right? You most likely have an ester, a carbonyl, and an oxygen right here, right? And I'm gonna explain these 2 hydrogens out for you. These 2 hydrogens here, right, are gonna be these 2 hydrogens right here because it's it's next to the most electronegative atom,
Okay.
oxygen right there, right? And we see that it has 2 neighbors, and its 2 neighbors are right here, right? And these 2 hydrogens right here and these 2 hydrogens right here are gonna be like this. These 2 hydrogens here has 4 subpeaks. Oh, that's not there. It should be 5 subpeaks, yeah, because that's 5 neighbors. Ooh. Yeah, we do not have that 5 subpeak 2 hydrogens right there. So there's something going on here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Because we don't have that peak on the HNMR right now. Like these 2 H's here should have 5 subpeaks because they have 4 neighbors. But we don't have that right there. We have 2 H's
Yeah.
here and 2 H's there.
So the structure's not correct based on that.
Yeah, based on the NMR, this structure is not correct. And also, this 1 hydrogen here is not supposed to be there,
Oh,
right?
yeah.
Because you know how we said earlier that these 2 hydrogens here and those 2 hydrogens there are 4, and they have 3 neighbors, so that's not supposed to be there. So I'm gonna redo this. Yes, this is difficult for sure. So I'm not gonna put that there.
really hope that
Wait, we're going to do movement here?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
From AA?
This is something weird.
Oh, so that's
3, 6, 2, is
Oh,
2.
that's on the human structure is my nightmare.
Can I check the thing? That's good. 2 H's there, 2 H's there.
half a sheet.
2 hydrogen seeing 2 neighbors, 2 hydrogen seeing 2 neighbors.
Yeah, I'm missing those two hydrogens right there somewhere.
Probably never. Because I know it's going to be my 12 one. So I don't care.
Oh my gosh. No.
Oh, yeah.
Oh yeah, yeah. Thank you. Yeah, let's try to solve this. 6 H's. This one. Alcohol. 2 neighbors.
Usually I just like draw the actual NMR. Like,
Oh yeah.
yeah, like the actual one on the, and then like start crossing it with their like.
Yeah, let me erase the whole thing and restart my whole thought process on this. And if I can't get it, I'm gonna look at the key and analyze it and move on to the next thing. Yeah. Okay, time is it? Okay, yeah, this is gonna be the last part here because we're spending too long on this one.
I'm so sorry.
No, it's okay, it's okay, it's okay. This is a difficult one for sure. Okay.
Like actually draw the NMR.
Actually, I'm just gonna draw the NMR out like this.
My phone is me.
See, 1, 2, 3, 4, 5, 6, 7, 8,
Yeah. No, yummy.
9. So 3, 6, 8. That's 9. That's gonna be 1 hydrogen. That's gonna be yeah. Say this is carbon. This is the alkene with only 1 neighbor. So it's gonna be like that. And that 1 neighbor is gonna be like this, and put an OH right here. And now from here, I'm going to put that 1H. This is the alcohol, and that 1 neighbor there. This is gonna be 1 neighbor, 1 neighbor. This is 1 neighbor. This is gonna be spectroscopy 1H, 2 H's. And it's 2 neighbors here with 2 neighbors, and that's gonna be because I know I have an alcohol somewhere, but Yeah. 3, 6, 8, 10, 12, 14, 16, 19, 22, 24, 26, 27.
No.
Oh my gosh. Yeah. Okay, let's just analyze the key and see
Okay.
what the key says. Yeah. Yeah, this yeah. Let me try to read the key, what it is. And we'll move on to alcohols.
What's nice is there's actually no
I don't know what to look. Is this?
Oh my god, it's like that. You see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
This is gonna take me like an hour.
Oh my god, and it's coming out like that. Okay, so you know how when we were trying to work through this, we had this looking structure as a fragment for sure. We had this one correct earlier with the ester, and then we had the alcohol present. So if you get the DOU correct and you have these fragments in place, like that ester with that specific group at the end, and alcohol somewhere, and this group, you're gonna get most of the points. Right, but if we weren't able to get this, we won't get full points.
Yeah.
Right, but we were able to get the alcohol. We were able to get the ester with this group and this group here. So partial credit.
Okay.
Partial credit, yes. But this makes sense now because
We have 14 carbs.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons
Yeah.
and 28 hydrogens. 2, 4, 6, 8, 10, 12, 14, 15, 18, 21, 24, 27, 28.
Yeah.
And 3 oxygens. 1, 2, 3. Yes, and we have alcohol here, carbonyl here,
Okay.
and oxygen right there. And it makes sense now because like everything in the HNO1 makes sense as well with the number of neighbors.
Yeah.
Right? You know how before when I tried to predict the molecule, we had that one peak with 2 hydrogens that's gonna have 4 neighbors, right? But we did not have that peak there, right? All of the hydrogen peaks here would agree with the HNMR now, right? So that's the hardest part, I would say, like agreeing
Yeah.
with all the HNMR sub peaks.
Oh,
Yeah, but getting the fragments and functional groups is okay, but piecing it together in this specific format here is the hardest part. Yeah, so that's like spectroscopy right there. Yeah. Yeah, it's like uh-huh. Right. Oh, the 2 hydrogens here, right? Because they're between 1 and 2, it's these 2 hydrogens and that 2 hydrogens right there. The 2 hydrogens next to the alcohol right here is this one right here. Yes, or this one. Yeah. Right. It's difficult. I know.
Thank you so much.
Yeah, of course.
Do some-
Yes. I'm gonna do some 8B stuff, which is gonna correlate with 118A, hopefully, like alcohol stuff. Yeah. Yes. Let's do 8B stuff now. Are you guys in 8B? 8B? Okay. Are there any like questions, topics you guys want to go for 8B? Yeah.
Actually, from my
Yeah. Uh-huh.
assignments, I'm quite don't understand like the mechanism of tertiary alcohol from alkenes.
Tertiary alcohols to form alkenes.
Yeah.
With what reagents?
With strong acid.
Strong acids. Okay. Tertiary alcohols to form alkenes.
Like that is using HOSO4.
It's just a point heat,
Yeah.
right? So let's talk about that. That's gonna be dehydration of alcohols, right? And you don't have to have a tertiary alcohol, but we'll start off with a tertiary alcohol. So if we have something like this, and we react it with H2SO4 and heat, this is a big sign of dehydration of alcohol, right? Especially with the heat. Now, we have a strong acid, the first step is to protonate this OH using the H2SO4. Right? And that's gonna give us this right here. Before, this OH here is a bad leaving group.
Yeah.
This is a good leaving group now.
Because it's hard.
It's charged, positively charged. And when it leaves, it's gonna leave with that pair of electrons, and it's gonna leave as a neutral water molecule, which is stable. If this leaves, this is gonna leave as an OH minus, which is not stable. So the point of the first step here is to convert this bad leaving group into a good leaving group by protonating it with the strong acid we have. Now think of this as an SN1E1 type mechanism. What is the very first step of an SN1E1 type mechanism?
The leaving room needs to detach.
Yeah, the leaving group detaches or it just leaves by itself.
Yeah.
It goes away by itself. When that happens, what happens to the charge of this carbon here?
It becomes positive.
Yeah, it becomes positively charged, which is a carbocation intermediate. And whenever you form this carbocation intermediate here, you gotta always stop and watch out for any rearrangement step, like a hydride shift or methyl shift, right? Stop, watch out for rearrangement steps. See if you could make that carbocation more stable or not. Is it already at its most stable position, or can we move it somewhere to become more stable?
I don't think it could move.
Yes, it cannot move because this is a tertiary carbocation. It has 3 substituents attached to it already.
It's already like the most stable condition.
Most stable condition for 118A, yes, for now.
Yeah.
With this one here is secondary carbocation, that's less stable. We don't want to move it there. This one here is primary, less stable. We don't want to move it there. This one here is also primary. We don't want to move it there. So we stop here. We don't have to worry about that rearrangement step. Okay, now.
Sorry, I have a really quick question. Can you do a hydride shift?
You can, but it's going to become unfavorable reaction. We don't want it to do that, right? Because if we do a hydride shift, the carbocation is going to become less stable, less substituted, right? Because when we think about carbocations here, this is a methyl carbocation, this is a primary carbocation, secondary, tertiary. The more substituted the carbocation is, the more stable it is, right? Stability. Stability.
So if the carbocation is already on the
Most
stable,
position,
then we don't move it.
then you don't move it. You don't worry about the carbocation shift rearrangement,
Okay.
right? And there's a very specific term that describes this thing here. What factor is that? It starts with an H. Hyperconjugation. Does that sound familiar? Have you guys learned about the term hyperconjugation? Yeah, so that's because of hyperconjugation. And if you guys want to understand why that's the case, right? Think of these carbons here as donating electrons to that positive charge, because there's like orbitals there, donating electrons to the positive charge, making it more neutral, more stable. Whereas this methyl carbon here has 0 R groups, 0 donating groups, so it's very angry, very unstable. This one here is more happy, more stable, because there's more R groups donating electrons to it, making it more stable, more neutral. So the more friends this positive charge has, the more stable it's going to be. The less friends it has, the less happy it's going to be, less stable it's going to be. Right? Now, when we have heat, what reaction is going to be major? SN1 or E1?
E1.
E1, yes. Right? Because usually when we do SN1 E1 reaction, the SN1 is major over E1, unless you add heat. Right? Heat is going to favor the E1 reaction. So this is. So for Levens, she says this is the substrate carbon, and these are the alpha carbons, 1 carbon away. But this is actually the alpha carbon, and these are the beta carbons here, like how most classes teach it. For Cagley, did she go over any of that? Didn't go over it? Okay, so just to stick with Levens class, and I'm just gonna say this is the substrate carbon here with the carbocation, and the alpha carbon is the first carbon away from the substrate carbon right there, right? I'm gonna draw out at least 1 alpha hydrogen for each alpha carbon. Alpha hydrogen, alpha hydrogen, alpha hydrogen. Let's say this is A, B, C. Which one do you want to grab to make the more stable alkene, the more substituted alkene? A, B, or C? A, the most substituted one, right? And the base that we're gonna do is the HSO4 minus that we kicked out earlier. That HSO4 minus is gonna be our base that comes back to grab hydrogen A, form a double bond right there to give us our tri-substituted alkene. If we grabbed B or C, we're gonna form this alkene right there, right? And this is less stable because this is a di-substituted alkene. The more substituted the alkene is, the more stable it's gonna be, right? So if this is carbocation stability, this is gonna be alkene stability here. This is unsubstituted. This is mono substituted. These are di-substituted. This is tri-substituted. And this is tetra substituted. But for the di-substituted, these are similar. This is more stable. This is the cis alkene. This is the trans alkene. And this is the gemino alkene. Right? And stability will also increase from left to right. Right? Because the more substituted the alkene is, the more stable it's going to be. That's why we chose hydrogen A to grab to form the more substituted alkene, the tri-substituted alkene, right? Because it has 3 groups attached to it. 1, 2, 3. Whereas this alkene here has 2 groups attached to it. That's why this is more stable. That's why we grabbed hydrogen A instead of hydrogen B or C.
Wait, so what is B and C make?
B and C makes this right here,
Which is
a gemino alkene, where the 2 R groups are on the same carbon.
okay.
Right.
Okay.
The cis alkene is going to be when the 2 R groups are on the same side of the alkene, like that. Right. So this is dehydration of alcohols on a tertiary alcohol. Okay. Any questions on this before I give you guys another tricky problem here? That is going to be more tricky than this problem here, but similar reaction, same reaction. No? Okay. Let me give you guys. Wait, who's that? What? Oh, what? Oh my god. I don't know. I don't know what was. What? Let me check my phone. Oh my god. Okay. Now. Okay, try this problem out, predict the product, and draw out the mechanism. And then I'll come around to answer any questions you guys have, and then we'll come back to this later.
Can I do it on the other side of the whiteboard? Because my binder is running on those papers.
Yeah, you could do it on the other side of the whiteboard. Are you guys from OChem class or which class? 118A. Cagley or Levens? Cagley? Okay. You guys are learning this reaction too, right? Dehydration of alcohols? Okay, that's good, that's good. 8B as well, so this is gonna help everyone. I know. Yeah. I know, like she uses like Levens stuff. Yeah, I know. Yeah.
I go to lectures.
Yeah.
The only funny thing is after an exam, she'll pass the mic around
Yeah.
the room for feedback. I'm oh, how was the quiz? Yeah. And everyone is either complaining or.
Who was that?
I think they know you.
Why did they leave it here though? You guys have any questions? Any questions? Okay. Okay, sounds good. Hi, do you guys have any questions on anything? Mm-hmm. Yeah.
I don't recall like learning about this in her class. Like I don't know. I don't understand what this is.
I see.
Yeah.
um, did you learn about anti-periplanetary transition state by E2 reaction?
I don't think
You don't think so? Okay, okay.
Yeah, I'm an 8B.
You're an 8B? Oh,
Yeah.
so that's Levin's,
Yeah,
right?
yeah.
And this is from Levin's practice
Yeah, she said like to study
quiz?
everything.
Study
But I don't
everything.
remember learning about that like at
Uh-huh.
all.
And this question here is asking you to
It's just like
circle the more stable structure,
yeah.
intermediate. And this is a carbocation. And then this is gonna be
I don't know.
that.
Does this matter? Like, what is this?
That symbol there is transition state. So this right here is a transition state for the reaction.
Okay, a transition state?
Yeah, transition state. Yes. And you're gonna circle the most stable structure, most stable transition state,
Okay.
right? And this is gonna be relating to that reaction right there, because once we protonate the OH, right, that becomes OH2 plus. That's
Okay.
this good leaving group right here. And you know how once we have that OH2 plus, the leaving group just leaves off by itself, right? Because we're in protic solvent, like a lot of water is just gonna like grab the water and kick it out right away. So it's just gonna leave by itself, forming that
Okay.
carbocation right there.
I see. So this would be the more stable because this one has the leaving group that's more willing to leave.
More willing to leave, yes.
Yeah.
This is not an aprotic leaving group like bromine or chlorine or iodine or something like that,
Okay.
right? If it was bromine or chlorine or iodine, this would be the more stable transition state.
Yeah, but
Right.
because it's OH2,
Mhm.
it's not as
Yeah,
stable.
there's aqueous solution flowing around, which is gonna grab that water and just make it leave, kick it out right away in
Okay.
protic solvent, right? So this one here would be more stable. But can I check the key for this before I move on?
Yeah,
Because I don't
yeah.
want to like give you the wrong
This is the key.
answer before I move on. Yeah. But that's
This
my.
is
Oh, this is the key.
Oh.
Concerted E2 it avoids primary carbocation. I see. Oh my gosh, I see. Because you know how in that mechanism right there, once we have the good leaving group, we leave to form a carbocation intermediate.
Mhm.
What kind of carbocation intermediate is this right here? That's another thing you have to keep in mind. Like how many other carbons is this carbon attached to?
Just one.
Just one. That's a primary carbocation.
Yeah.
It's too unstable to be formed. It's too unstable to exist. So we cannot form that at all, right? Which is why we're gonna do an E2 reaction instead. Like this leaving group here is not gonna leave by itself first, because if it leaves by itself, it's gonna form this carbocation.
Okay.
That's super unstable. That's a primary carbocation.
yeah.
So instead of doing an E1 type mechanism, we're gonna do an E2 type mechanism, where the leaving group just grabs the alpha hydrogen, makes a double bond here, and kicks out the leaving group at the same time.
I see. But that's what the dashes are for. They're like representing which
Right.
one's leaving.
Those dashes are gonna represent this minus carbon hydrogen, create a double bond here, kick out the leaving group at the same time,
Okay.
and that avoids any carbocation intermediate,
Yeah.
because we're not kicking out a leaving group first. We're just doing an E2 reaction right away.
Yeah. Okay.
Right.
Good
So
to know.
that's the reason why. Yeah.
And then okay, so
Uh-huh.
whatever has a primary carbocation
Carbocation.
Yes.
Yep.
will just be the most unstable because that's the most unfavored, right?
Yeah, that's the most unstable, like the primary one or the methyl one.
Okay.
Right. If this was a secondary carbocation, however, like if there was another R group there, then this would be formed. This would be able to form,
Okay.
because this is a secondary carbocation now, because this carbon here is attached to two other carbons,
Mhm.
1 and 2.
Okay.
That's good. But because it's only attached to one other carbon, this is not able to exist. Like it's too unstable to exist. Right. So that's why we don't go here. We go here.
Okay.
I get it.
And then this is the reason why.
Yeah. Concerted E2 avoids the primary carbocation.
Okay.
Right. This primary carbocation here, too unstable to exist. Right.
Mhm.
But if it forms a secondary or tertiary carbocation, then you would go here.
Okay.
Right. I didn't keep that in mind, but that is very important as well. Primary or CH3 methyl carbocation, too unstable to exist.
Okay.
Yeah.
Thank you.
Yeah, of course. Yes. I'll get you after. Or I think actually she would ask a question first, but I'll come to you after. Yeah.
Yeah, I just
Uh-huh.
I'm a little lost on like
Yeah.
their cleavages.
Yes.
I'm from Catholic section.
Catholic
so I'm
section,
taking
yeah.
women's practice,
Uh-huh.
so
Right.
I'm just confused confused on like what patterns we should look out for because I just really didn't know how to.
How to approach that? Yeah. This one here, did she give you a pattern on like the thing? Like actually, there is a very specific thing for this, like the ranking system for this. So I'm gonna go over this and the whiteboard next. Go over this exact problem here with other reactions, right? Yeah, because this one here is gonna require me to explain like the different scenarios and everything.
That would be really helpful.
Yeah, that's good. That's yes. Uh huh.
I'm like, sugars, I'm so confused.
I might.
You can't grab the hydrogen from the carbocation directly, right? You can only grab the hydrogen one carbon away from the carbocation because that's able to make the double bond right there. If you tried grabbing this hydrogen here and you create a double bond right there, that's gonna break the octet rule for that carbon, right? Because this carbon here has 2 hydrogens. If you create a double bond right there, that carbon will have 5 bonds. 1, 2, 3, 4, 5, right? So it has to be this one or this one or this one. So they're all gonna be tri-substituted.
I don't remember right.
Is that problem right there? Oh, yes, yes. Okay, that's one of the products. I just realized that there's another product that you can form as well, and I'm gonna go over that right now. Yes. Did you guys work on this problem here? We got the same answer. Yes.
So this is a
Secondary carbocation,
which is why there's a hard
hydride shift to form a carbocation there, and then you grab the hydrogen to make it double bond there. That's correct. Yes. Leaving group carbocation. Wait. Sorry. What was your name? Sorry.
Ming.
Ming. So your arrow here. How is the arrow? What is the arrow here? What direction is it going to?
Going to the center carbon.
Yeah. We cannot draw an arrow like that, right? Because the arrow represents the movement of electrons. There's no electrons here. So you have to draw out the invisible hydrogen and shift the hydrogen over to that carbon right there.
Oh, I see.
Right? And that's the hydride shift. We're moving that hydrogen over. Which you create this carbocation right here, the more stable carbocation. Right? This is important for mechanism problem because she's gonna grade the direction of the arrows, the form of charges, and like the correct number of carbons. So that's good. Right? And this right here, right, is gonna make the most stable carbocation. But I just realized that you can also grab this hydrogen here to create a double bond there, which will give you this alkene here. And they're both equally stable.
Why?
Because this alkene here is tri-substituted, and this alkene here is also tri-substituted.
Oh, and it both cancels the carbon.
Yes.
So if there was a carbocation here and you move this,
Yes, they both
they
would
both
cancel.
would cancel.
Yes, because we're adding a bond to that carbon in each scenario.
Okay, so both would work.
Yes, both would work. And both are equally substituted. So these are 2 different products right there.
But this one is a secondary carbon,
This.
and that one is primary.
Yeah.
feel like it
Oh, this
would-
is also secondary. Because it's attached to 2 carbons. This one and this one.
Oh, I see.
Yeah, it's just outside of the ring.
Okay, I see.
Right.
Yeah.
So these are your 2 different possible alkenes right here. Yeah.
So I'm like, this one's very similar to the one you showed us, but how come in this case
Ah.
it forms ether?
Yeah, now it's gonna form an ether because we're in low temperature.
Oh, so that's
Right.
considered lower. I'm like, oh,
135.
Degrees for Levitz is low, 180 degrees for Levitz is high.
okay.
You're in Cagley?
Leave in.
Okay,
for
so-
8B.
Oh, for 8B. Did you go over this reaction?
Yeah.
Okay,
No, this
okay.
is the final exam.
Final exam?
Yeah.
Okay, so you definitely do need to know this right here. Let me go over this actually right now and then go over
Okay.
the ether reaction after.
And then later, would
Yeah.
it be possible to go over sugar reactions?
Sugar, yeah, I could go over sugar reactions as well. Yeah, for 8B. Yeah, that's good. I'll do the sugar reactions in this 118B section. But I'll do 118A for now. Yeah.
Yeah.
Yeah. Okay. Let me see the. Uh, uh, Hmm.
Brian, I have a question.
Yes.
Are you doing tutoring next fall?
Next fall? Yes, I am.
Okay.
Uh-huh. I could let you
Okay.
know more information here.
Because I didn't find out about this till like 2 weeks ago.
Yeah, of course, of course. Wait, are you in 8B, right?
Yeah.
Wait, so are you gonna take 8B over this
Well, I don't know.
fall?
I'm not doing good right now.
Oh, shoot. Okay, okay. I see, I see. Yeah, yeah. But I will be still here at the fall throughout the whole year. Yeah, yeah. Uh-huh. Yes. Wait, how did you find out about this?
I actually started looking at the Discord.
Oh,
Yeah.
I see, I see. Yeah.
Yeah, Discord, but I fear I was too late once I actually started.
Started the Discord? Yeah. Oh my gosh. Did you find my other review session videos for the quizzes, the previous quizzes this quarter? Oh, sure, yes. Like that would definitely help you as well.
Is there other videos?
On my YouTube, yes. Yes, it's on here, like my YouTube.
Oh, okay.
Yeah, yeah. Like it's for 118A, B, and 8B this quarter. Like there's review videos for those classes this quarter. Yes, of course, of course. Yes. What was your name? Sorry.
Oh, Maggie.
Maggie. Yeah. That's oh yeah. Didn't you show up to my review
to the
office
couple-
hours?
yeah, the 2
Oh,
office hours.
that was you. That's
Yeah.
you. Oh my gosh. Okay. Okay.
Yeah.
Let's see. Let's see. HX reactions with ethers. This is an 8B reaction, right? This one? Right? HX is going to be, where X can be chlorine, bromine, or iodine. Fluorine is not going to react with that. It's too unreactive. Right. Now,
118A.
yeah, this is 118A2, the end of 118A. And an ether is going to be this functional group here. Do you guys know the difference between ether and ester?
Ester is the one with double bond oxygen next to it.
Yes, carbonyl, just like this. Right. Keep in mind the difference between amine and amide as well. Right. Okay. So then, selectivity. I'm just gonna give you guys the chart first, and then do practice results afterwards. Tertiary is the highest. Methyl is the second highest. Primary, unhindered, and then primary, hindered, and then secondary is the least. Right, and here's the chart. Depending on what your OR group is, you can have a methyl, CH3, primary unhindered, primary hindered, secondary, tertiary. And that's going to tell you what reaction you have. Right, and that's going to be primary hindered. Right, and this is going to be SN2, and this is going to be SN1, where E1 is minor. Okay, let's look at some practice problems here. Yes, like the one that you showed me earlier, which is going to be like this. If we have OCH3 reacting with HBr, this is an ether because this is ROR. This is HX, where X is Br. So this is when we use this list and this chart. My two R groups are going to be this carbon here, directly attached to this oxygen, and that carbon right there, directly attached to that oxygen right there. This is a methyl group. This is a primary unhindered carbon. Do you guys know the difference between primary hindered and primary unhindered carbon? Okay, let's go over that.
It's when something is attached, it's hindered.
Yes, attached to the next carbon.
Okay.
Right. Primary unhindered is like, let's say we have an X group like, that we're interested in. This carbon here is a primary carbon because it's only attached to one other carbon. But that one other carbon is only attached to like one thing, right? A primary hindered carbon is going to be when we have something like that or something like this, right? Because this carbon here coming off of the group that we're interested in is also a primary carbon, but the carbon next to it is branched. It has at least 2 branches coming off of it, making this a primary hindered carbon, right? And Levens for sure makes a big deal out of this because she could be definitely tricky, which this chart covers all of those reactions between the primary unhindered and primary hindered reactions as well, right? And back in like winter 2024, like 1 year ago, I was like the concept review leader for 118A, and I made like notes on Levens 118A stuff, so I could share you guys this folder with all the notes and practice problems here for you guys after. Yeah. Yeah. So let's analyze this. If we're comparing primary unhindered versus methyl group right there, what takes priority?
It's unhindered.
Versus methyl.
It's S. Oh.
Wait, before we choose the chart, we choose which group is going to do the reaction. Methyl, yeah, because methyl here is higher than primary unhindered. So we look at this chart at the methyl row, which is going to do an SN2 reaction, right? SN2 like reaction. So what's going to happen here is, wait, let's see here. Bromine. Leaving group. Wait, hold on. Tertiary, primary unhindered. Tertiary, primary unhindered. SN1. SN1. Yeah, tertiary, primary unhindered. Yeah. Was there a key to this problem here? I want to double check before I move on to the next thing. Yeah. Okay. Yes. Because I was like, I made the key right here, but this is a typo right here. This is not right. That's right there. Okay, that's good. That makes sense now. Yeah. Uh-huh. Oh, there are alkenes in there? Yeah. Oh yeah. Oh my gosh. Oh yeah. I heard about that. Yeah, she like left early and she took a 5-minute break as well. Oh my gosh. Yeah. So for the mechanism, right? The first step is to protonate the oxygen with the strong acid we have. So this oxygen here is gonna grab this hydrogen, kick out the bromine, and give us this right here, right? Now we have 2 good leaving groups here. This could be our good leaving group, or this could be our good leaving group, right? Meaning that if that green group is the good leaving group, this is the substrate. If the blue is the good leaving group, this is the substrate right here, right? So that's why we choose this ranking list right here to choose which one is going to be our substrate. Because the methyl is higher than primary unhindered, this is our substrate, this is our good leaving group, right? And the reason why it's SN2 like is because what happens when we kick out that group right away? What kind of carbocation gets formed when this whole green good leaving group leaves? What kind of carbocation gets formed here? CH3+. It's a methyl carbocation that's too unstable to exist, right? a methyl carbocation or a primary carbocation is too unstable to exist. So what's going to happen next is that the Br minus here is going to do an SN2-like reaction where we're going to attack this carbon and kick out that leaving group to give us our final answers, which is this alcohol.
I thought that OH was not a good leaving group.
OH is not a good leaving group, but this is OHR plus with a positive charge, right? When it leaves, it's going to leave as a neutral charge, which is stable and a good leaving group, right? If that was like not there, if the H was not there and the positive charge was not there, that's a bad leaving group.
Oh, so this whole thing is a leaving group. This whole thing is a
That whole thing is a good leaving group. The whole green outline thing is the good leaving group right there,
Okay.
right?
So do we decide that it's an SN2 reaction first, and then we decide which one's the better leaving group, or how exactly does that process work?
Yeah. So the process here is gonna be first
I know what happened last time.
choose the prioritized substrate from
Oh, yeah.
this list right here. Second,
Oh, no,
use chart for reaction, and then you do the reaction.
Yeah, I think maybe then. It's like you can teach me.
So when we like write, when we write the final answer, do we do like this plus this, or do we just write this and that's fine?
If you have to write this and this, both
Okay.
is organic and both would be formed, so you have to include both for the full credit.
Okay.
Mhm. Yes.
Thank you.
Yes.
I have another question.
Uh-huh.
So when we look at the chart for the reaction, this represents this part. So when we're looking at
So the substrate here is going to come directly off of the oxygen atom,
yeah.
right? So this represents the primary unhindered, and this represents the methyl group
So
right
when we're
there.
referring to the chart,
Uh-huh.
the R/R1 that represents the substrate.
Yes.
Okay.
Yes.
Okay. Okay.
Mhm, yes. Let's do another one just for practice.
Yeah. Let me see if I can.
Uh-huh. Oh, these are the keys. These are the
That
keys.
is weird.
Oh, right, right,
I'm
right,
just
right.
trying to find the weird ones.
Yeah. I think B is also weird. Wait, actually, no, never mind.
Maybe we can try
E?
Yeah.
Okay, let's do E.
Yeah.
Mhm. This one here.
Yeah.
1, 2, 3, 4. Okay,
Yeah.
got it.
Yeah.
For me, it's
Yeah. Okay.
Yeah.
Okay. Any questions on this before we move on to the next one? Okay, let's move on to the next one. You guys have to know synthesis as well, right? Like the synthesis reactions? Oh my gosh. Sorry? Williamson ether synthesis? Yes, you do need to know that as well. 1, 2, 3, 4. Okay. Try this out, and I'm gonna walk around and answer any questions you guys have.
Well, I also went to last lecture. Yeah, he said that. I think someone asked me. It's gonna be synthesis.
I'm feeling good. Yeah. Wait, is this yours?
No, it's yours.
Who brought it? Who put it there?
No, I moved it because when you moved the box.
Oh, I see, I see. But who was that? That guy you were doing? Oh my god.
Just take guess.
Okay, okay. Wait, let me see who texted me. That might say it's for me.
But you consider this reaction called ether cleavage, right?
Um,
Ether cleavage, or just HX reaction with ethers?
yeah, HX reaction with ether. Oh, ether cleavage. Yeah, ether cleavage. Yeah. with strong acid. Nucleophilic acid,
Okay.
HX.
Oh. Oh, yeah, I sent my exam too.
Huh?
I sent my exam too.
Oh yeah,
Yeah,
yeah.
have you see it?
Not yet, but I will. I will. Yes. That was the one where the average is 42%, right? Okay, I'll take a look at that later. Oh my gosh. You got it now? That's good. What was your thought process behind this? How did you work through it?
I literally just did what you told us to, and then
Uh-huh.
I first I found the
Substrate, yeah.
right? And then I went through the chart.
Right.
Then I got S1 V1, so
Mhm.
that's one.
Right. Because this is a tertiary substrate versus a
Yeah.
primary anhydrous substrate, and based on that ranking list, the tertiary substrate takes priority. Then once you look at the chart, it's an SN1 reaction. So when you protonate it, you use that as an electrophile, and you kick out that whole group out as a leaving group, forming a tertiary carbocation. And then the CO minus comes back to attack that tertiary carbocation to form that final product right there. And that's the SN1 major product. E1 is minor, which is
Yeah.
going to form this minor alkene right there. So if you use this whole chart, then you should be able to do the ether reactions.
You may have explained this before.
Mm-hmm.
Sorry. How again do you determine the priority for the substrates? Like why?
Why it's like that?
Yeah, why is it like that?
Yes, it's because the tertiary substrate, right, is able to form the most stable carbocation that we know so far,
Oh.
right?
Oh, okay.
Whereas the methyl carbocation is gonna do SN2 reaction. So this is just experimentally determined. Like they just found it like that.
Okay.
Yeah, just accept it. Yes,
Sure,
yes,
okay.
yes.
Alright.
Yeah, there is another chart for alcohols
Uh-huh.
with the same reactions, like HX with alcohols,
Uh-huh.
but the ether one is more complicated for sure. Yeah. Uh-huh.
Sounds good.
Yes. Okay.
One thing does it change like whether like the nucleophile that we have like for instance HI, H1, what if we had like H2SO4 or something? Does anything change when we have that? You said it was a good one, so I'm looking at it again.
Yes, this one here is not going to be that reaction. This is the dehydration reaction we went over earlier, right? But that dehydration reaction was with alcohols. This one here is now with ether. Right? So this is a different chart than this one here, right? And let me find that chart. I think I have it here as well. There's so many charts actually. Yes, this one here. Yes. Uh-huh.
Because like I definitely know how to use H2SO4 when we have an alcohol and we want to make it hydrogen.
Yeah.
Or we want to make it water so it leaves.
Uh-huh.
But with ether, I don't remember.
Ether, I know.
So
It's crazy.
I think if I have that chart, I'm probably good.
Yeah, and then I also like numbered out the different letters under that specific problem, and then B was in it, like B, F, N, T, X, Z, A, F is on there as well. Yes, that's good.
Seriously, I wish I had your
This is the 118A notes that I made when I was a content review leader for 118A.
Yeah, it's just like chart.
Yeah. But there's one typo on one of the problems here.
I don't think I did it right. But so this is a
Okay. Were you guys able to get this problem at the bottom?
I thought I'm getting it. But
Do you want to try it? This one here? Yes. You want to write it down?
I could try to
Yeah. Let's see it.
write it, but
Describe your thought process as well. Like talk through the thought process.
Oh, so
Oh, you can do it here. You can do it here. You can write it down here. Let me move back. This right here.
I feel like it's gonna. It's gonna start attack
Yes.
from here.
Protonate the oxygen
Yeah, and we have us over here.
with the hydrogen. So draw out the bond
Oh yeah.
to the hydrogen that I just picked up. Yeah.
And that should be very ready to leave.
Yes, because we have two substrates there.
Yeah.
This one, what is that substrate?
Tertiary.
Tertiary. What is this substrate?
Secondary.
How many other carbons is this
Oh
attached to?
yeah. One.
One. So it's primary. But what kind of primary is it? Is it primary unhindered or primary hindered?
Unhindered.
Unhindered. What is higher in priority?
It's 3, so it will
3. So it's gonna do
detach this way. Wait, wrong direction. Okay.
yes, wrong direction. It's gonna go kick off that whole group right
Yeah.
there. So draw out the carbocation that you just formed. Positive charge right there. The oxygen is no longer there
Oh.
because
I
we
see.
kicked that whole group out, right? So what you're gonna form is this right here. So draw.
Wait, this one is not a carbon cation. That one is just like an alcohol.
No,
Oh,
no, we kicked that whole group out.
Oh, I see. I
Yeah,
see.
so it will become a carbocation. Yes. CP useless.
It will be like something like that.
Yes, and draw out the alcohol that just kicked out, that just left.
And that one is going to be grabbing this chlorine over here and finish like that.
Yeah, that's good. You got it. So you could use this chart to figure that out right there.
Yeah.
Yeah. Uh-huh.
You're doing Chem AB and distribution color? That sounds terrifying.
Uh-huh.
I do this to be like.
Hmm. Yeah, so it's not going to be like this. You try doing SN2, right? Where you use this as a nucleophile to attack that carbon and kick out the whole living SN2 mechanism.
Okay, wait, so
The reason why we don't do that is because we have an ether
this
here.
makes sense. Like,
This is one living group, which you used.
yeah, just starting.
This is another living group.
This makes sense.
That means we have two possible substrates.
Yeah.
This carbon versus this carbon. What kind of carbon is this?
Tertiary?
This one?
Yeah, no, primary.
Primary, and
then
is it
from
primary
there-
unhindered or primary hindered? Is this carbon unhindered?
Right, well, with this
Looking at the chart right there, what takes priority
Oh, primary unhindered.
versus tertiary?
Oh, tertiary.
Yes. And if you look at the chart over here, what reaction would it do? SN1. Yes. So this is our
And then would you also
substrate
add
right here once we protonate that. So if this is SN1, this is our whole living group right here. Like that whole thing is our good living group, but we're just gonna kick it out first to form the carbocation.
Okay.
Yes.
Oh,
Of course.
And then this,
Oh, and Ming, these were the major products. She might want you to draw the minor product as well.
So that's going to be an alkene.
Yes, alkene. So when you have this carbocation right here, the Cl minus can grab this hydrogen from an alkene there and give you this alkene right there. But this is minor.
So for exam, I saw like only
Major.
major product.
Yes, but this showed up on the answer key, so I just wanted you to know that, just in case.
And on the answer key,
On the answer key of this practice. But that's for the practice. On the exam, you probably won't have to draw that out for the exam, so don't worry about that for the exam.
And just ask me, are we going to reach epoxide in the first session?
Epoxide. Oh, this is 8B, right?
Yeah.
In the first section, let's actually do epoxides right now.
Okay.
Epoxide right now spinning. Yeah.
My biggest question is, epoxide, like when you open up the epoxide,
Open up the epoxides in acidic conditions versus basic
yeah,
conditions,
it's gonna
right?
react differently under acidic and basic conditions.
Yes, it
And
is.
I'm wondering, like, what are generally considered acidic or basic?
Yes, yes.
Because like there's some HS minus, which is FO, MP or something.
MCPBA,
MP product, so like HS
Uh-huh.
minus.
H.
And will it react like for in acidic or basic conditions
Uh-huh.
for epoxides?
Yes, I'll go over that with you
Okay.
here right now
Yeah.
for the remaining of the session. Yes. Okay.
so elimination.
This one here is SN1 reaction, Hey, Aniket. How's it going? How are you?
How are you doing?
I'm doing fine. How have you been?
I'm doing pretty good. Just studying for finals.
Studying for finals? Yeah. Are you feeling ready for it? Or like, no, not.
I
Yeah.
feel okay.
That's good. Okay. Yeah. That's good. So
Should we use the other side?
we have two substrates here.
Yeah.
This one versus this one.
Yeah.
What kind of carbon is this? Tertiary. What kind of carbon is this?
Primary.
Yes. And there's two types of primary. Is it primary unhindered or primary hindered?
Should be. Is it unhindered?
Unhindered, right? Because the next carbon is unbranched. There's no branch there,
Yeah.
right? So when you're comparing these two substrates, you use this ranking list right here. Tertiary beats primary unhindered.
Oh.
So you look at this chart right here.
Yeah.
Looking at the tertiary side, we're gonna do SN1 reaction, right? So when we protonate the oxygen to create this good leaving group here, we have two possible good leaving groups, right? This is a good leaving group right here, or this is a good leaving group right here, right? But because tertiary one, this is our substrate, making this the good leaving group, right? This thing here is the good leaving group.
Yeah.
So when we do SN1, we kick that out from a carbocation. This is one of the major products, and then SN1 is major,
Yeah.
creating this final product. E1 is minor, creating this minor product.
The E1 is minor. Wait. So the O gets kicked out, or the OH gets kicked out, right?
The whole ROH gets kicked out. Yep.
But the minor, why is there an H connected? Yeah. And then
Yes. There's H's connected to all of these carbons here.
Yeah.
But when we do E1, we grab one of the H's. It could be here, here, or here.
Okay.
It doesn't matter because it's symmetrical.
Yeah.
Forming a double bond right there to create the E1 product. But for the exam, you don't have to draw that out because it's minor. You only have to draw the major product for the exam.
Okay.
Yeah. Mhm.
Sorry, you go.
Oh, you guys go first. I'm just asking
Oh,
the college
okay.
side, which is not so
Oh, okay.
important.
Could you explain how the E1 mechanism worked again? Because like I have this as the major product from the SN1, right?
Yes.
How does
Uh-huh.
the E1 create?
Where did you get that methyl group from?
Wouldn't it be here?
Oh, so when we kick off the bond, right? This whole bond here, the two electrons of that bond goes onto the oxygen. So this oxygen here is positively charged because it has 3 bonds. Right? This oxygen is positively charged because there's 3 bonds. 1, 2, 3. When it kicks off, there's 2 electrons in this bond. The 2 electrons go into that bond to create this here. Right? Because before this oxygen here only had 1 pair of electrons.
Okay.
Right? But when it leaves, it now has 2 pairs of electrons and it's now neutral.
Okay.
Right? So the final product would not have that
Okay.
as the answer. Yeah. And your question was
How does the E1
minor. Oh, right. So the E1 minor will come into play when, once you have this carbocation right here, right? The Cl minus will attack that carbocation to create this major products here. That's SN1.
Mm-hmm.
But if you want to do E1, that's the positive charge right there. You want to pick one of the alpha hydrogens. This is alpha carbon, alpha carbon, alpha carbon. It doesn't matter which alpha hydrogen you pick because it's symmetrical. Everything is the same. Let's pick this one here. Cl minus is going to grab that hydrogen, right? Forming HCl. The bond here between the hydrogen being grabbed and carbon, it would go here to create this minor product, which is the E1 product.
Okay.
Right. Elimination reactions always creates double bonds, like E1, E2. Reactions creates double bonds. Substitution reactions, SN1, SN2, creates like substituted products. Yes.
Okay.
Yeah.
Thank you.
Uh-huh. Uh-huh. Yeah. Yes. Uh-huh. Synthesis? Yeah. Let's do synthesis problem. And then we'll do 1 and 2, and then we'll be done with the session for 118A. Yeah. Of course, yes. I do have one extra hoodie, so I could give it to you guys if you guys are interested in doing tutoring sessions with me next quarter. One extra one, but it's okay if you guys still are not interested.
I'm sorry?
I do have one extra hoodie that I'm gonna be giving out
Oh, okay.
for people who are interested in tutoring with me next quarter.
Okay.
Right? Because I'm giving it to the people who are private tutoring with me, but one of them can't make it, so I'm gonna give one of them out
I
to
see.
someone. Yeah, to someone. Yeah. Let's see here. Where's the eraser? Right here. Synthesis. Okay. Let's see. Let's see. Do you guys have a strategy for these synthesis problems? Like, you guys have a thought process on this, or have you guys practiced with a lot of synthesis problems there, or no, not yet?
The first thing I'm going to do is trying to figure out what kind of hierarchy we're using.
What kind of reaction we're gonna do?
Yeah.
Yeah, you could think of it like that, right? Or you could go backwards and find the similarities and differences. So let me go over my thought process on this synthesis problem here. The first thing I do is find the similarities between this molecule and this molecule here. I see that this 1, 2, 3, 4, 5 carbon ring is the same as this 1, 2, 3, 4, 5 carbon ring right there. That's the similarities between those two molecules. The differences are going to be this alcohol, that bromine, and that R group right there. Now I think about what reactions can make those differences. So we have a new R group there that was not there before. What reaction do you guys know that adds an R group to the molecule? Hydrocarbon train. This is one of the newer reactions.
Oh, this is the
Grignard reagent, yes, which is RMGBr. This is going to be the R from the RMGBr, right? But the Grignard reagent can attack 3 things: a haloalkane, an epoxide, or carbonyl, right? So before I go over that, let me show you this common Grignard reagent here. Let's say this is MGBr, and give you these 3 reagents here. Say we have this Br, this epoxide, second step acid workup, or this carbonyl right here. So for Grignard reagents, the carbon directly attached to the magnesium is partial negative charge. That's my nucleophile. For these reactants here that you need to know that can react to these reagents here, they're going to be the electrophiles, right? The first reaction here, our electrophilic carbon is this partial positive carbon here with that good leaving group right there. Now, the second reaction here is going to be epoxide opening. And in epoxide opening, we can open it up in the acidic conditions versus basic conditions. Acidic conditions is going to be when you have a strong acid, like H2SO4 floating around somewhere, right? Basic conditions is going to be when you have negative charges floating around, like OH minus, OR minus, Grignard reagents. This Grignard reagent here is a strong nucleophile and base. So when you see Grignard reagent, think of basic conditions. And in basic conditions, do you guys remember if we're going to open up the epoxide in the less subside or the more subside in basic conditions? Less subside, yes. Because think of it like SN2 reaction. SN2 prefers to attack the less subside, the less sterically hindered side, right? So it's going to be this carbon right here, not that carbon. this carbon is going to be my electrophile because it's less sterically hindered, less substituted, right? Now, if we have this carbonyl right here, this carbonyl carbon is my electrophile because it's partial positively charged, right? Because it's attached to this electronegative oxygen, making it partial positive charge. So all these dots right here that I just dotted out are my electrophiles. This star right here is my nucleophile. So I'm gonna number these reactions: reaction 1, reaction 2, and reaction 3. So looking at reaction 1, the mechanism is gonna look like this. Well, what do you guys think it's gonna look like between this star and this dot? This star is the nucleophile, this dot is the electrophile. What's gonna happen between those two molecules?
And then the BR.
Yes, SN2 reaction. The MgBr dissolves into ions. It disappears. It just floats away when that happens. You don't have to draw that in the product. So this is why I star my nucleophile and dot my electrophile. It helps me connect the two pieces together. So when I connect the two pieces together, this is my starred carbon. This is the new bond between the star carbon and dot carbon. This is new. That came from this attack right here. When a star attacked the dot, it created that new bond between the star and dot. Right there. That's our new carbon-carbon bond. So that's when you see new carbon-carbon bond, you think of Grignard reagents. Right?
Sorry, how do oh, so the BR completely leaves, so we only have one bond that's new.
Yes. But this dot carbon here is attached to this methyl group right here, or whatever the R group is. It could be methyl group, ethyl group, propyl group, isopropyl group, tert-butyl group, sec-butyl group, whatever it is, attach it onto the dot carbon. Because I have that methyl group there, draw that methyl group coming out like that. If it was attached to two methyl groups, draw two methyl groups coming off of the dot carbon. Right? Because this whole molecule right here is this whole molecule right here. This is the star carbon of that molecule. This is the new bond between the starred carbon and dot carbon. That bond was not there before. We made that bond right there.
Okay.
But this dot carbon has that methyl group, which is this methyl group right here. The BR is no longer attached to the dot carbon because we kicked it out. Right? For example, like if we have an isopropyl instead, like that, we attach an isopropyl there, like that. Because that whole isopropyl is attached to the dot carbon.
Okay.
Right there.
Okay.
So this is the new bond right there. So let's just do that, and that's gonna give us that product where this is the star carbon, this is the dot carbon. Now for the second reaction, we have the same Grignard reagent. And this time we have an epoxide. And you could open up the epoxide in two ways, like we said. Oh, the more subside or the less subside. In this case, it's gonna be the less subside because we're in basic conditions. This Grignard reagent here, because it has a negative charge, it's a strong base. So this star here is gonna attack the dot and kick out that bond onto the oxygen right there. So this is the tricky part here, connecting those two pieces together. When that happens, we're gonna have this structure where this is the star carbon. This is the new bond between the star carbon and dot carbon. New bond. Right? The dot carbon is no longer attached to the oxygen. That bond was there, but we popped it up onto the oxygen. The two electrons in this bond here are gonna go onto the oxygen right there. Right? But this carbon here is attached to a methyl group, and it's still attached to the oxygen right here. Like this bond right here is that bond right there. And because the oxygen was neutral and it's gaining a pair of electrons, it's gonna become negatively charged right there. Right? Because before it had 2 pairs of electrons, it now has 3 pairs of electrons. It gained the 3rd pair of electrons from that bond right there because there's 2 electrons in that bond. Right? To make it more clear for you guys, if this was the green carbon right here, which is attached to the red carbon, that's this green carbon right here. And this green carbon here still is attached to the oxygen, which is that bond right there. but we broke that bond between the red dot and the oxygen right there, like that. So that's the connection between the star and dot carbon, and how we open up the epoxide like that. Any questions on this before I move on?
Sorry, I like visualize it like this.
Mhm.
So if we like open it up here,
Uh-huh.
it would be the O is to the right,
Uh-huh.
right?
Yep.
And then this is this, and this is this.
So this is this carbon, this is the
This one.
dot carbon, right? And when we open it up, we're gonna do anti-parapenetrant resistance, let's say. So we're gonna open it up and do backside attack. So the new bond here is gonna go down because if this bond is going up relative to this bond, the new bond has to go down right here, right? Because imagine this as your reference line bond right there.
Yeah.
This bond is going up.
Right.
The new bond is gonna go down because we're doing backside attack. So let's erase this bond right here
Okay.
and draw a bond going down. And that's the starred carbon. And this is the new bond between the starred carbon and dot carbon. From this attack, this arrow here creates that bond,
Okay.
right? Now we draw what's attached to the starred carbon.
So just
1, 2, 3, 1, 2, yeah, 3
1,
carbons.
2, 3.
Yes, like that. Now this oxygen here is now negatively charged.
Yeah. Okay. I
Right.
see
Mhm.
it.
Yes. That's if there's stereochemistry involved, but because it's a synthesis, we are not worrying about stereochemistry here. That's like a whole other thing when you do backside attack, right?
Okay. I think I'm just
Uh-huh.
confused from like this little like thing with
Mhm.
this. So this just because BR like
NGBR
NGBR
goes away.
completely goes away. So this
This bond here breaks onto the oxygen.
and the new like a completely new bond form.
Yes, from the star and dot carbon,
I see.
right? And this bond here
This like goes
becomes
to,
a pair of electrons on that oxygen,
okay.
giving the oxygen a negative charge now.
Okay.
Yeah.
And then for here, a new bond forms as well over.
Mhm. Star and dot. Yes. Yes.
Because the BR leaves. And so
Mhm.
this is like switched like that.
Yes, it's switched like that. This isopropyl group on the dot is this isopropyl group here, but it's switched like
But
that.
then this bond is still this bond.
Yes.
Okay.
Yes. Mhm.
Okay.
Yes. Okay. The last step here is to protonate the O minus to become neutral OH. Like that H3O plus is this H3O plus second step right there. This is acid, H3O plus hydronium ion. That's going to allow for this O minus here to become OH, neutral OH. Acid-base reaction. And that's gonna become OH like that. And this is the star carbon. This is the dot carbon right there, like that. Okay. Yes. Any questions on the epoxide opening with Grignard reagents before we move on to the carbonyl? Okay, let's move on to the carbonyl one. So this is my starred carbon still. This is my dot carbon now. What's gonna happen here is that this star carbon is gonna attack the dot carbon, and we're gonna make a new bond between the star and dot carbon. But there's gonna be a problem here with the dot carbon. If we don't do anything else, right? This dot carbon is gonna have 5 bonds, right? 1, 2, 3, 4, 5, with the new bond between the star and dot. So to conserve the octet rule, we're gonna pop this double bond onto the oxygen. We're gonna move one of the bonds of the double bond onto the oxygen, creating an O minus, O negative charge. Yes, and that conserves the octet rule. So when we connect it, this is how I'm gonna connect it. This is the star carbon. This is the dot carbon. This is the new bond between the star and dot carbon. This dot carbon right here is that dot carbon right there. Before, it was double bonded to an oxygen. It's no longer double bonded to an oxygen because we popped that double bond onto the oxygen. It's now single bonded to an O minus. This oxygen has a negative charge now because the electrons from that bond went onto the oxygen. This dot carbon here still has 2 methyl groups. 1, 2. And that's how we connect the star and dot molecules together with the carbonyl. Then we bring in our acid worker step, H3O plus, to protonate the O minus to become OH. Right? And that would give us this final answer right here. Where this is the star, this is the dot, right there. Like that. Right. That's a lot. It's a lot, I know.
Thank you so much.
Mhm. Yes, that wasn't even like the synthesis yet. That's just one of the reactions to the synthesis problems. So, yes, you got the synthesis, Wiley?
Yeah, we had that good news.
Good news, yes.
That carbon.
Uh-huh. Right. Okay, let's take a little break. Let's see. Hey, Elysia. Oh. Wait, was that you that gave me the boba? Oh my god, I was like, oh. That was Elysia.
I didn't want to follow you, but I didn't want to give it to you.
Oh my gosh, yeah, thank you.
Yeah.
Thank you.
What is your order?
It is
Well, I know that.
mango green tea.
Is that your order? Because I got that for you, and I just like picked something that
Random?
I thought was like, 'cause that's good.
Yes, I like it. Yes, I like it. Thank you.
Is that your go-to order though?
Is my go-to order?
Or like, what is your?
My go-to order for it. I don't really go to 2%, but I like it. Yeah.
Yeah. No, I mean, like, what's your go-to order in general?
In general, I usually get fruit tea. So this is perfect. This is perfect.
Because I know people like do like milk tea.
Milk tea.
People don't.
Yeah.
I just felt like today was like a fruit type of day.
It is, yes, because it's more refreshing than milk tea, I think. Like milk tea makes me dehydrated, fruit tea makes me more hydrated. So this is perfect. Thank you. It's okay. It's still perfect. Right. Did you bring your hoodie?
Yeah, I did.
Yes. Okay. The pictures are gonna be very soon. Yeah. Thank you. Okay. So the next thing here is that we know this is a Grignard reaction, right? So that means that this is my star carbon, this is my dot carbon, and this was my alcohol right here, right? So we know that this was a carbonyl, but the Br came from an alcohol because we know when we open it up, the carbonyl, it becomes an alcohol. So let's go backwards. This is retrosynthesis. If I go backwards here, I'm gonna get this molecule here, right? Where this was my starred carbon of the Grignard reagent, the MgBr. This was my dot carbon, which this alcohol came from the carbonyl like that, right? Where this was the dot carbon right here. Now let's fill in the reagents. What reaction do you guys know that would convert this secondary alcohol into this ketone? Oxidation. What reagents? There's 2 reagents that you could use here. PCC or Jones. PCC, gang, yes. It's easy to write out. That's gonna oxidize the secondary alcohol to the ketone. Now, this second reaction here, right? We can bring in this Grignard reagent like this, where this is gonna be the star carbon, 1, 2, 3, 4. That's way too many carbons. Second step, acid workup, right? And that's gonna create this right here. Because if you guys think about the mechanism, right? This star carbon here is gonna attack the dot carbon and push the one outside oxygen. This is the new bond right here between the star and dot. Now, what reaction do you guys know that will convert this alcohol into the bromine? It's gonna be a very weird reagent. Yeah, what reagent will convert this alcohol into the bromine? HBr? Oh yes, that is one, right? HBr. Doing fine, how are you? Okay, HBr is one, right? And we don't have to worry about carbocation rearrangement because once this becomes OH2 plus, we form a carbocation. When the OH2 plus leaves, right? This becomes a carbocation, and the Br minus can attack that carbon right there. But this is very risky because if this was a secondary carbon and you had a tertiary carbon here, you would do a hydride shift. Right, but in this case it worked out. We don't have to worry about that. But to be more safe, if you don't want to do any hydride shifts and you want to convert alcohol to Br, you're gonna use PBr3.
Oh yeah.
Right.
Because it just removes the OH and puts Br.
Yes.
And what kind of mechanism is that?
That SN2-like mechanism, but it's not SN2 mechanism, but it's gonna be like SN2, right? She probably did go over the mechanism, but that's a no quite thing. Right? If you wanted chlorine, right? In this case, you could use HCl or SlCO2, and that's gonna give you this right here, Cl, like that, right? That's if you wanted this as a final product instead of bromine. So there's 3 reactions in the synthesis here: oxidation, second, Grignard, third, HX with alcohol, or PBr3, SN2-like reaction, to convert this molecule to that molecule right there. Okay, that's it. Okay, break.